This is section 2.8. 2.8 is about inverses and determinants. Now, if you remember in section 2.6, we found inverses. In section 2.7, we found determinants. So you can predict in section 2.8, they're going to combine those two concepts and give you some properties and some theorems. Let's take a look. Section 2.8, inverses and determinants. All right, we begin section 2.8 with a theorem. The theorem says if A is invertible, then A inverse is unique. If A is invertible, then A inverse is unique. Now, if you remember the way that we determined if A was invertible or not is we just tossed it into a matrix with the identity matrix on the right and then kept working with it. If we were able to get it to the point where we had I on the left, then we had A inverse on the right. So some matrices we found we couldn't even get to that point. So some matrices aren't invertible. So what this theorem is telling us is that if A has an inverse at all, there's only one inverse. I don't have to think about maybe there's another matrix that I can multiply on each side of A, on either side of A, and get I. There's only going to be one if there's one at all. All right, another theorem in this section. If A is an n by n invertible matrix, then, so A is square and it has an inverse, A inverse is also invertible. Now, what's it mean to be invertible? It means it has an inverse. Well, so A inverse inverse would be A. Now, the reason why that happens is because when two matrices are inverses, I can multiply them in either order and get the identity matrix. Well, obviously, if I multiply A inverse by A, I'm going to get the identity matrix. Therefore, the inverse of A inverse is A. All right, another part of the same theorem, so I still have the same premises. I have if A is n by n and it's invertible, then if B is also an invertible matrix, so if B also has an inverse and B is also the same size as A, it's n by n, then the product A times B is invertible. AB quantity inverse is equal to B inverse times A inverse. Now that confuses a lot of people as to why they need to switch places like that. A lot of people want to say, well, it would be A inverse, B inverse, but no, it's not an exponent. It's different from an exponent. If, you know, I had the letter A and the letter B and -1 was an exponent, then sure, yeah, it would be, you know, the letter A to the -1, the letter B to the -1. But it's not letters, okay? It's not algebra. It's matrices. So A is referring to a matrix, B is referring to a matrix. So the inverse of AB is B inverse A inverse. Now the reason why is because if I multiply A times B inverse times A inverse, things are going to line up correctly. The B and the B inverse are beside of each other. Those two would then cancel out. That would leave the A and the A inverse beside of each other, and those two would cancel out and give me I. Okay, and if I were to reverse the order, if I put B inverse A inverse first, and then times AB, the A inverse and the A match up, they're touching each other, and if they're touching each other, they're going to cancel out. And then that's going to give me B inverse, whoops, I have those in the wrong order, sorry about that, B inverse times B, and then that's equal to I. So that should be B inverse times B instead of B times B inverse, sorry about that. Okay, another part of this theorem. Again, A is square, A is invertible, then if K is a non-zero scalar, then K times A is invertible, and the inverse of Ka would be 1 over K times A inverse. Now the reason it works out this way is because I want to have something that I can multiply times Ka and get I. So in other words, I need for the K to cancel out. How do I cancel out a K to get a 1? I use the reciprocal of K. So K times 1 over K would cancel out. Then I'd have A times A inverse. That's going to cancel out and give me I. All right, let's take a look at an example. A inverse is the matrix 1, 0, 0, in the first row, second row, -2, 1, 0, third row, 5, -4, 1. And B inverse is the matrix 1, -2, 0 in the first row, second row, 3, -3, -1, third row, -6, 2, 7. And the instructions tell us to find AB quantity inverse. Now I have known people who have taken A inverse and gone to the trouble of reducing that down with the identity matrix on the right and finding A. And the same deal with B. They've taken B inverse and found B. Then they multiply A times B. Then they take that new matrix and find the inverse of it. But we have this theorem, right, that makes this process much easier than that, much shorter. That whole process I mentioned before would take, what, 15, 20 minutes? Okay, we can do this very quickly because we know that AB quantity inverse is B inverse A inverse. So let's just take the B inverse matrix times the A inverse matrix, because those two were given, and then just multiply it out. If you take the first row of B inverse times the first column of A inverse, as you see, you get 1 times 1, -2 times -2, 0 times 5. Add that together, you do get a 5 in the 1, 1 position. You continue on, going rows times columns, and you'll fill up the matrix at the bottom with 5, -2, 0 in the first row, 4, 1, -1 in the second row, and -10, -1, 2 in the third row. So much easier than trying to find A, then trying to find B, then multiplying them together, and then trying to find the inverse. It's a mess the other way. Okay, another theorem in this section says that the determinant of A times B is equal to the determinant of A times the determinant of B. Now obviously for this to work, AB is going to have to be a square matrix, A is going to have to be a square matrix, and B is going to have to be a square matrix. Okay, I couldn't say that the determinant of like a 3 by 4 times a 4 by 3 would be the determinant of those individually. So all of these quantities have to be defined for this theorem to work. Okay, let's look at an example how we would use this theorem. Suppose the determinant of A is 2 and the determinant of B is -4. Find the determinant of A squared B. Okay, according to the theorem, the determinant of A squared B should be equal to the determinant of A times the determinant of A times the determinant of B. Well, the determinant of A was given to be 2. The determinant of B was given to be -4. Now, I have no idea what A and B even look like, but it doesn't matter because I was just asked for the determinant. So the determinant of A squared B is -16. Didn't have to know a thing about the matrices other than what their determinants were equal to. Okay, another theorem in this section. Like I said, they're giving you a lot of properties, theorems about inverses and determinants. This theorem is extremely important. The theorem says it says A is invertible, then here's the if and only if the determinant of A is not 0. Okay, now what that means is A is invertible if the determinant isn't 0. It also means the determinant isn't 0 if A is invertible. So the if and only if in the middle makes it go both ways. One implies the other. The two terms are equivalent, essentially. So A has an inverse if its determinant isn't 0. And if I happen to know its determinant isn't 0, that's a guarantee that I can find an inverse. This is going to come in pretty handy because if you remember, finding inverses took a little bit of work. So if I have some clue somewhere that the determinant is 0, I don't have to bother with trying to find an inverse. There wouldn't be one. Okay, in addition to this, the determinant of A inverse is 1 over the determinant of A. In other words, the reciprocal of the determinant of A. Okay, let's take a look at an example here. Find the determinant of A inverse B if the determinant of A is given to be -2 and the determinant of B is given to be 3. I want the determinant of A inverse B. Okay, now according to the first theorem about determinants, it said that would be the determinant of A inverse times the determinant of B. And then according to the previous theorem, the determinant of A inverse would be -1/2, because it's the reciprocal of -2, then times 3, which is equal to -3/2. Okay, another example. Find x so that A is not invertible. Okay, now remember, if A is not invertible, its determinant must be 0, because we said if its determinant wasn't 0, it was invertible. So we can put knots in front of both of those. So if it is equal to 0, if the determinant is equal to 0, it's not invertible. So let's take our A matrix that they give us to be x minus 1, 3, 3x minus 1, and let's set the determinant of that matrix equal to 0. Okay, the determinant of that matrix would be x minus 1 times x minus 1 minus 9. We said that's equal to 0. From here, it's just algebra, right? We just want to multiply out x minus 1 times x minus 1 and get x squared minus 2x plus 1, then minus 9. Work that out, x squared minus 2x minus 8. Conveniently, this factors into x minus 4, x plus 2. From the x minus 4, we get that x would be 4. From the x plus 2, we get that x would be -2. Okay, so we figured out for that A matrix that was given to not have an inverse, that the x values would be 4 and -2. We'll use that theorem a lot more too, besides in just finding the determinants, finding the values, that make it not invertible. You'll find values that make it invertible. We'll also be able to determine, because of some other things we've learned and things we'll learn in the future, we'll be able to determine how many solutions a system of equations might have, just based on the fact that the determinant is a specific value. So that's an extremely important theorem. And even though there aren't a lot of problems on section 2.8, it is an extremely important section. So make sure you learn these theorems, learn the properties, practice a little bit, and everything will be okay.